So today we're going to be looking at the birthday problem, also often called the birthday paradox. And so this is a pretty canonical problem seen in a lot of introductory probability courses, and it kind of incorporates a lot of the different techniques of probability problem solving. And in general, I think it has a very elegant solution, and we'll kind of see how we arrive to that. Formally what the birthday problem is asking us is, in a group of, n people, what is the probability that at least two people in that group share a birthday? So, you can imagine the setup is that you're at some birthday party, and there's, some amount of people there, and what you're looking for is the probability that at least two people in that group share a birthday, okay? So we're gonna assume a couple things before we go ahead and get started here. So the first thing we're gonna assume is that the probability of a given person's birthday falling on any day of the year is equally likely. So I have a 1 in 365 chance of my birthday falling on any day of the year. Okay, so we have a uniform distribution over all the days of the year. The second thing is that we're going to assume that there's no leap years in this world. Okay, so and that just makes the math a little bit easier. So we always assume this 365 days per year, which allows us to use this probability for our first assumption. Okay. The third and final assumption that we're going to have to make here is that people's birthdays are independent and identically distributed events. Okay, so what that means is my birthday and the day it falls on has no effect on when your birthday might be. Okay, in reality, this isn't necessarily true. I think it's been shown that people tend to have more babies in like the summer seasons, and so that means that there is some sort of correlation, which implies some level of dependency between people's birthdays. But for the sake of this problem, we'll assume that these are independent events. Okay, right into the math here. So just again, to kind of make it clear, what we're looking for is the probability that at least two people share a birthday, right? And so the way that we should start thinking about this is basically in terms of a probability space, okay? So recall, a probability space is basically all the possible events that can occur and their associated probabilities. And we know for sure that the sum of all of those individual probabilities of the events in the probability space is going to be 1, right? So what we can think about is, okay, well, there's the probability that 0 people share a birthday, right? Then there's the probability that, hey, maybe like 2 people share a birthday. 1 doesn't really work in this case, right? Then there's a probability that, okay, maybe 3 people share a birthday, or maybe 4 people share a birthday. And we can kind of create these many different partitions all the way up to n people, all n people in the group sharing a birthday. Now, the odds of this are extremely low, but it is a possible event that can occur, and it has some non-zero probability, and therefore it is part of our probability space, right? And so by partitioning our probability space like this, now we can consider what partitions in this probability space comprise this event that at least 2 people share a birthday, right? And if you think about it, actually almost all of these events are part of this larger event that at least 2 people share a birthday. Because if 2 people share a birthday, then at least 2 people have shared a birthday. And if 3 people share a birthday, then at least 2 people have shared a birthday, and so on, right? And so actually all of these different events here in our probability space are part of this event that at least 2 people share a birthday. So if we call the probability that we're looking for, the probability that at least 2 people share a birthday, let's call that P of A, then the sum of all of these individual events, right? The sum of their probabilities will be P of A, right? Now, that is a little difficult to calculate, right? Because we see that, we're going to have to go through many different events here and calculate their individual probabilities if we hope to find P of A. But what we have now is a partitioning of our probability space, where P of A is on one side, and this other event, the probability that 0 people share a birthday, is on the other side, right? And we know that this is some other event. Let's call that, let's call the probability associated with that event P of C. Then we know that PC plus the event that at least 2 people share a birthday, PA, these must sum to 1, right? These must sum to 1. And that just comes from this right here, the fact that the sum of all the probabilities in our probability space must be 1. And from this, we can, very easily solve that P of A, therefore, is just equal to 1 minus PC, right? So find the single probability, the probability that no people share a birthday, we can actually find P of A, the probability that we're looking for, the probability that at least 2 people share a birthday, okay? So I hope that's clear. So this is where we are, right? We figured out that PA is actually just equal to 1 minus PC, where PC is this complement event, okay, that no one shares a birthday. So how are we going to solve for PC then, right? So if we solve PC, we get PA, so let's solve PC. So PC is basically saying, okay, well, we can't allow any 2 people to share a birthday. That means that the first person can have a birthday on any day of the year, right? They have all 365 options available to them. But then the second person, well, he only has 364 options because the first guy picked a day. And if we want to maintain that no one shares a birthday, then the second guy can't have his birthday fall on the same day as the first guy. So now he has 1 less option. And then similarly, the third guy will have, 2 less options. He only has 363 choices for his birthday. And we can do this all the way up to the nth person. 365 minus n minus 1 are the number of options that nth person has, such that we maintain this criteria, okay? And this is basically this product right here rewritten in just a very nice compact way. And so this is basically, it's a analog to the sum notation. This is basically saying the product from I equals 0 to n minus 1, where 365 minus I over 365 are the terms of that product, okay? So if you look, when I is 0, this term just resolves to this. And when I becomes n minus 1, which is the final term in that product, this term just resolves to this, okay? Cool. So what we've done is we've used the complement rule to basically say, okay, we're going to look for this other probability PC, and here is a very nice clean way to write it, okay? So now we have a equation for PC, but how are we actually going to, what can we do with this, right? This looks rather gnarly. So what are we going to be able to do with this, right? So the first step, the first little trick we're going to use is the fact that when we take a log of a product, what we actually get is a sum of logs, okay? So that sounds a little confusing, but it's actually very elegant. So when we take the log of PC, and PC is just this product right here, right? So when we take the log of that product, what we actually get is now a sum of logs, right? So a log has been added to each term here, and now we're just taking a sum of those log terms. And this holds for basically any product that you take a log of that becomes a sum of logs of each term. Okay, and this last step, we've just basically kind of rewritten this fraction as 365 over 365, which gives us that 1, and then minus the I over 365. And that gives us the final term here. Okay, cool. So what we've got now is basically a rewritten version of now not PC, but it's log PC, right? So we found a way to write log PC in terms of these log terms. And the beautiful part is now we're not working with products, we're working with sums. And that's going to make things very nice for us, okay? So where do we go from here, right? So we have a sum of these log terms, but how are we actually going to be able to resolve this sum requires an aside into what you might have learned in calculus as the Mclaren series. Okay, so the Mclaren series basically provides an estimate for E of x. Okay, and you might be wondering, where is this coming from? Why is this random series showing up here? But it actually very elegantly fits into what we need to resolve up here. Okay, so the Mclaren series basically tells us that E of x, and this is actually just the definition of E of x, is actually just 1 plus x to the 1 over 1 factorial plus x squared over 2 factorial, and so on, right? So the kth term here is actually just x to the k over k factorial, okay? So this is actually just by definition of what E of x is. And you can see that we can estimate E of x when x is really small with just these first two terms, okay? And so why is that? That's because, imagine my x is really small, right? So imagine my x is like 0.5, right? Then my x squared is going to be like 0.25, right? And then I'm also dividing that by 2. So you can see that, as x becomes smaller and smaller, the square of x becomes even smaller, right? And so when I have a really small x, it's sufficient to estimate E of x with just these first two terms, because this third term and so on will just become so small in the numerator that there's really no need to include them in the estimate. Okay, so what we've basically said is 1 plus x, right? This is an estimate for E of x when x is really small, okay? And we can actually see that, right down here when we graph these two functions out, right? So this right here is E of x, and this line is 1 plus x. And you can see that when x is really small, like in this domain, that these two functions are generally very, very close to each other, right? And that's all that this math is basically saying. It's saying that this function is a good approximation for this function when the domain x is really small, okay? And for us, that x is going to be very small, and we'll see why, right? So what we've gathered so far is basically two crucial facts and a third that I'm going to add right now. So again, to recap, the first fact basically came from our remolding of what log PC is into this sum of log terms. And the second fact just comes from what we showed above with the Mclaren series, where E of x is well approximated by just the first two terms 1 and x if we have a small x. And again, that just comes from what we showed up here. So this third term is actually just a fact which holds true for basically the sum of natural numbers, right? So when you take the sum of the first n natural numbers, so 1 plus 2 plus 3 all the way up to n, what that results in is actually just this term right here, n times n plus 1 over 2, right? And so this is all that's being said here. It's when you take the first n natural numbers and take their sum, this is your result, okay? And this is just a useful sum that you should know. So let's actually use these facts to then kind of resolve what PC is, right? So that's ultimately what we're looking for. So using fact 2, we're going to be able to rewrite what is actually inside these log terms, okay? And the way we're going to do that is basically, if you look at the structure of this actually looks a lot like 1 plus x, right? Where x is just negative I over 365. And below here in fact 2, we say that e of x is well approximated by 1 plus x, and so 1 plus x is also then well approximated by e of x, right? So applying this fact kind of in reverse, we can rewrite this as e to the negative I over 365, where again, e of x, where x is just negative I over 365. So this is all to basically rewrite what is inside these log terms in terms of e, okay? And the reason we want it in terms of e is because log and e are inverse functions, right? So when you take the log of something and then you exponentiate that, they kind of undo each other. So if we can get a exponentiated term in this log, the log will actually become undone, and it'll make our sum a lot easier to actually calculate. And so that's precisely what we're going to do in this part. So using fact 1, we're going to be able to rewrite this log PC. Now, substituting 1 minus I over 365 with actually just what we found here, e to the negative I over 365, okay? So now we're taking the sum of the log of e to the negative I over 365, and log and this exponentiation, they're going to undo each other, and that holds in any case, right? So when you have the log of, and this is log base e, right? So log base e, also known as the natural log. So when you do e to the anything base e, you're just going to get x back, right? This is a property that holds for log. So lucky for us, we're going to be able to undo the log and the e and just get this negative I over 365. So now we've really kind of cleaned up our sum a lot. So let's do one last little bit of work here, and that's basically just pulling this negative 1 over 365 multiplier out of the sum, because it has nothing to do with I, it doesn't need to be in the sum. And so now all we've really got is just a sum from I equals 0 to n minus 1 of I, okay? So that's basically just 0 plus 1 plus 2 all the way up to n minus 1, where n minus 1, of course, depends on your group size, right? So now this should immediately strike you as sum of, the first n natural numbers. And so we're going to be able to use fact 3 here, right? This useful sum, except we have to be a little careful about the indices, right? So here we're summing from k equals 1 to n. Here we're actually summing from I equals 0 to n minus 1. So there's some index offsets there, right? So instead of n, we're just going to have n minus 1, right? Because we're going up to n minus 1. And then instead of n plus 1, we're just going to have n, because n minus 1 plus 1 is going to give us that n. And again, just divided by 2. So basically, this sum is rewritten right here as just this product. Okay, n minus 1 times n over 2. And this again just comes from fact 3. And then we have this negative 1 over 365 multiplier because we had already pulled that out. Right? Cool. So now we're getting somewhere, right? Because now we don't have a sum, we don't have a product. All we have are these two different terms being multiplied together, and they're just a function of n, which is our input size, right? Our group size. So basically, what we're saying is we've solved log PC as a function of n, okay? So now we're going to work backwards to now solve PC and then to ultimately solve PA, which is the probability we were looking after in the first place, right? So let's go ahead and do that. So what we're going to do is we're going to basically retrieve PC by exponentiating on both sides now, okay? So by exponentiating on the left, we simply get PC, right? So I'm just saying E raised to the power of whatever is on both sides. And then on the right, we basically have E to the power of all of this, right? And all of this was just what was on the right-hand side there. So now we have a solution for PC, and now we just need to do one last step to get to PA. Remember, PC was the complement probability in that probability space. So 1 minus PC is going to get us PA, which is the probability that at least 2 people share a birthday, right? And so we can do that last little bit right here, and we see that PA is actually just then 1 minus PC, right? Where PC we calculated to be this whole thing. Hopefully, all that math, kind of sits well with you. Let that marinate in your head a little bit, and think about what those steps were that we took to get to this final solution. We've basically found, what is the probability that at least 2 people share a birthday. PA, we found that as a function of n. So now, if someone were to come up to you and ask you, hey, I have a group of size 30, and I want to know what the probability is that at least 2 people in that group share a birthday. Well, we could very easily calculate that for them now. Plugging in n as 30 into this expression, we could give them P of A, which is the probability that there is at least one match. And I think, just the steps that we took to be able to give such an elegant solution to this probability, I think is very beautiful. And I think really captures the essence of problem solving with probability questions. So all the math being done and said, I want to actually, go one step further and actually take a look at what the theoretical probabilities are by group size of having a match. So here we've calculated P of A as a function of n, so we can very easily implement this as a function in Python, which is exactly what calculate prob is. So calculate prob is going to be a function which takes in n, a group size, and basically uses the exact expression that we calculated to return the probability that there's at least a match, at least one match within a group of that size. And we're going to go ahead and basically repeat this for all group sizes from 0 all the way up to 99 and look at what the theoretical probabilities are that we would expect from the math that we constructed. So as you can see here, for groups of size 0 or 1, the probability of at least 2 people sharing a birthday is 0. And that makes complete sense, right? If you have less than 2 people, you don't even have a second person to match with. As we, get to 2, we see our first non-zero probability, And you can see, as n increases, how does the probability change? And I think what strikes most people as surprising when they first see this is that just when we get down to 23, we already are crossing that 50% mark of having at least one match. Meaning, in a group of size 23 or higher, you could say that they're actually more likely to have at least one match than not. And I think that that's really like confounding to some people. They don't intuit that. And that makes complete sense because, you don't originally think that this probability is going to grow so exponentially, but based on the math we did, you can see where exactly that exponential term comes into play and why, as your group size increases, your probability does as well, okay? And so we can actually go ahead and, plot these numbers here, and we see that plus 23 right here, we're already hitting that 50% mark. And by the time we're around, 40, definitely around 60, we're almost guaranteed a match, which is, I think, really cool. But, let's go even one step further because now we've constructed the math and we've done the theoretical calculations. So now let's run a simulation and see whether the empirical statistic that we see from running this simulation matches what theory tells us. So I won't go into this code in detail, but I'll give you the gist of it. Basically, what's happening is we're going to run a simulation which consists of 1,000 iterations. Basically, on each iteration of the simulation, we're going to slowly build our group up. And for each newcomer that comes into our group, we're going to assign him a random birthday, again, uniformly distributed. And we're going to see how many people our group can grow up to until we get our first match. And once we've gotten our first match, that means that we've had our first collision. And we're going to repeat this 1,000 times, basically to see, on average, at what group size do we have our match? At what group size do we satisfy the criteria of at least 2 people sharing a birthday? Okay, and you can see, that it is exactly what we'd expect, right? So around 20, close to 23, we basically have the mode that just matches the theoretical probabilities that we discovered.